In this video, we will discuss maps between manifolds in more detail than before, and especially the idea of carrying along tensor fields between manifolds using those maps. To start, let's consider the space of functions on a differential manifold n. Such functions take points q of the manifold n and map them to real numbers, which we call f of q, the image of q under f. Let's also consider another differential manifold M and the map between M and N, which we call phi. The map phi maps M onto N. The dimension of M and the dimension of N need not be the same. We also assume that this map is infinitely differentiable. In order to consider maps between tensor fields of the two manifolds, we have to start with functions. So let's consider a function f that takes a point P of the manifold n and maps it to a real number f of q. Since we have the map phi, and the map phi maps the point P to the point q, we can consider composition of the two functions and go from P to the same real number f of q. That defines a differential function on the manifold M. We call this function phi star of f, the pullback of f on M. This operation on functions on n can be thought of as a map between functions of n onto functions of m. Having defined the pullback of a function, we can make a map between tangent vectors at the point P to tangent vectors at the point Q. We will call this map the push forward of the tangent space at P to the tangent space of Q and give it the name phi star. Star is now a subscript instead of a superscript because it pushes forwards objects from the manifold M to the manifold N. Under this operation, any vector at the point P is mapped onto a vector at the point Q, which we call v star of v. Note that with the construction that we will discuss, there is no way to map the tangent space at Q onto the tangent space of P unless phi is invertible. In order to discuss the details, it is useful to consider coordinate systems. So first, let's consider a neighborhood of the point P and the chart that gives us the coordinates x mu of the point P. Similarly, a neighborhood of the point Q and the chart that gives us the coordinates y alpha of the point Q. The charts are invertible maps, and we can think of the coordinates of the point Q to be functions of the coordinates of the point P. Let's consider now any vector at the point P. This vector is an operator from functions on M to the real numbers. And we have already seen that if we take any function on M, then the operation of v on g is a real number which we denote by v of g. The pullback of f, phi star of f, is a function on M. Therefore, we know how to compute its image under the operation of the vector v. That will be a real number. That will allow us to define a vector at the point Q. In order to define such a vector, we have to know how this vector is acting upon any function f of n. So we define this action of the vector w on any function f on n to be the same as the action of the chosen vector v at the point P on the pulled back function phi star of f. Phi star of f is a function on m, v of v star of f is computable and is a real number. This seems quite abstract, so let's make it more concrete by computing the components of this pushed forward vector phi star of v. If we choose a coordinate basis d alpha, then the components of the vector phi star v will be given by this relation. And we know that the action of phi star v on any function f will be given by this relation here. So let's make a small digression and explain a little bit what we mean by this partial derivative of f with respect to y alpha. I have been a little bit sloppy in describing the image that we have so far. So let me be more precise in what I'm talking about. So we said before that the coordinate system in the neighborhood of P gives us the coordinates x mu of the point P. This is done by an invertible differentiable function which we call chi. Similarly, the chart that gives us the coordinates of the point Q will be a function which we will call psi. Then the maps chi and psi are invertible, so we are able to go, for example, from the point x mu in Rn to the point y alpha in Rn by considering the composition of those three maps. First, we use chi to the inverse of chi to go from the coordinates x mu to the point P. Then we compose that with phi to go from the point P to the point Q. And then we use psi to go from the point Q to the coordinates y alpha. That defines us the function y alpha as functions of the coordinates x mu. Similarly, we can use the charts to define functions that are functions of the coordinates. So here I am a little bit sloppy and I use the notation f of y alpha to actually mean this function here. So this function here uses the inverse psi to go from the coordinates of the point Q up to the point Q, and then f to go to f of Q. So we now have a map that takes us directly from the coordinates y alpha to the real number f of Q. And we will call this as f of y alpha. Similarly, the pullback of f can be considered as a function of the coordinates x mu. But actually what we mean by that is that we compose this map with the inverse chi. So we go from x mu using the inverse of chi to the point P, and then we use the pullback to go to the real number f of Q. So this will give us a function of the coordinates x mu. Another function that it will be useful to consider is the function f of y alpha of x mu. So here I'm a little bit sloppy in the notation, and by this notation here I actually mean this. what I do is I start from the coordinates x mu, use the inverse of chi to go to the point P, then I use phi to go to the point Q, then I use psi to go to the coordinates y alpha. So this is the y alpha of x mu that I mean here. But this is, then I have to use f of y alpha to get the number f of q. So after coming to y alpha, I have to use the inverse of psi, go up to q, and then go to the real number f of q. So that will help me explain what I mean by the derivatives that I write. So when I write here the derivative of f with respect to y alpha, what I actually mean is that I consider f as a function of y alpha by taking the composition of those two maps. Then it is useful to consider the derivatives of y with respect to x. In order to do that, I have to have y as function of x. And in order to do that, I have to use this composition of those three maps to construct this function, and then I can differentiate with respect to x. Similarly to the derivative of f with respect to y alpha, since the pullback of f is a function of on the manifold M, I can define derivatives with respect to x mu, the coordinates of P. But in order to do that, I have to have a function of x mu, and in order to construct this, I have to compose all those three functions. Take the inverse of chi, then use phi to go to the point P, and then use f to go to the point f of q. So the inverse of chi takes us from x mu to p, phi takes us from p to q, and f takes us from q to f of q. Then I can do this computation and compute the derivative of the pullback of f with respect to x mu. So this is actually the derivative of this function here, which can be written as this function here. You see here that I inserted the unit function, psi minus 1 composed with psi, so that is a trivial operation. But this function here is nothing but y alpha as a function of x mu. And then this function here will give us f of y alpha of x mu. So this is now composing functions on Rn in general, for general n, okay? And we can use ordinary real analysis, and the composition rule for derivatives will give us this result here. So when I write this, this is what I actually mean. So this is the final result, and now we can use this result to compute the components of the push-forward vector v. So this is the definition of the components. This is the action on a function f, and we have defined this number to be the action of v on the pullback of f. So this is nothing but this expression here, and we have computed this to be equal to this. So by comparing the two expressions here, we see that the components of the pushed forward vector v is given by this expression here. We can see that this expression here defines a linear operation on the components of v. So, this linear operation is represented by a matrix, and this matrix has those elements here. Let me be a little bit more explicit, since we will use this representation in actual computations. So notice here that the two indices are written clearly with alpha being the first one and mu being the second one of the matrix. So alpha represents the row of the matrix and mu represents the column of the matrix. So you see that the derivatives are arranged in the matrix as shown here. And this gives us an n by m matrix. Please forgive my typo here. Mu actually has to be an upper index here. So we can view this computation as being an operation on matrices. If we arrange the components of V on a column vector of dimension m, then the components of phi star v can be given in a column vector of dimension n by doing the matrix multiplication of the column vector v with the n by m matrix phi star. But here also the notation can be confusing, since we use phi star v also as the abstract notation for the vector. It should be clear from the context what we use each time. So let's summarize what we have done so far. We have two manifolds, M and N, a differential map of M onto N, which we call phi, where the point P is mapped onto the point Q. We are able to define a map between the tangent space at P onto the tangent space of Q by taking a vector V onto its pushed forward image phi star of V. And for that we used the pullback of the function f, so that the image of this function on M under V is equal to the image of f under the operation of the vector phi star v. This simplified diagram also gives us a simple overview of the situation. Here f of m and f of n are the differential functions on m and n respectively. The pullback phi star is a map from f of n onto f of m, and vectors can be considered as maps from f of m onto the real numbers and f of n onto the real numbers. So the vector v and the pushed forward image of it, phi star of v, maps functions here that are related by the pullback onto the same real number. We can use a similar construction to map one-forms between the two manifolds. Here we will see that we will be able only to pull back one-forms at Q to one-forms at P. Therefore, let's consider the dual of the tangent spaces at Q and P respectively. Omega is an arbitrary one-form at the point Q, and we will see how to map these onto a unique one-form phi star omega at the point P. We will call this phi star omega the pullback of the one-form omega. in order to define the pullback phi star omega, we have to remember that one-forms are linear maps from the tangent space to the real numbers. So omega is a linear map from the tangent space at Q onto the real numbers, such that any vector at Q is mapped to the real number omega of W. That can be used to define the pullback one form, which is now a one form at the point P. In order to define this one form, we have to define its action on arbitrary vectors at the point P. So we have to know what happens if we consider any vector v at the point P, which real number is mapped to with the pullback one form omega. So we will make the obvious definition, since omega is known, has an action on any vector at the point Q, which is known. We can use the push forward of any vector from the tangent space at P onto the tangent space at Q to compute this number here. Then we define the pullback of omega on any vector v to be equal to the number shown here. This map is linear and defines a unique one form at the point P. So again, let's make this construction more explicit by computing the components of this pulled back one form. This is the definition of the components, sorry, this is not the definition, this is the action of a one form on a vector v. It is related to the components of v and the one form with this relation here. And we can use the definition of the pullback to compute this number. So the image of v under the pullback form is equal to the image of the pushed forward vector v under the one form omega at Q. But we know that the components of the vector phi star v are these ones. Therefore, this image is given by this relation. So, the action of phi star omega on v is given by this relation, and we can read off the components of phi star omega. Comparing these two, we see that the component of phi star omega is computed from the components of omega by acting with the derivatives of the coordinates y with respect to x. This is again a linear operation which we now represent by this matrix here. Notice that star here is a superscript and the index mu comes before alpha. So, if we want to see this as a matrix operation, we have to construct a matrix that is now the transpose of what we had before. Mu now corresponds to the rows of this matrix and alpha to the columns. So, we can compute the components of phi star omega by arranging the components of omega on an n by 1 column vector, multiplying this vector by this n by n matrix, and obtaining the components of phi star omega arranged in an n by 1 column vector. So again, we have to make sure that we understand the notation. Usually by phi star omega, we denote the vector, not the matrix, and we see it here expressed as a linear combination of the coordinate one forms dx mu. And these are the components with respect to this basis. So, let's summarize again. We have the two manifolds M and N, the differential map of M onto N, P is mapped onto Q. Then we have defined a pullback of any one form, omega, at Q to a unique one form at the point P. And for that, we used the pushed forward value of any vector V, and we defined the U01 form by its action on V related to the action of the one form omega on the pushed forward value of the vector V. So we can summarize this in this much simpler graph. We have the two tangent spaces. They are mapped like this via the push forward function, phi star, or operation. And then one forms are maps of the tangent space onto the real numbers. And we see here that the pullback is defined so that omega and phi star omega takes us to the same real number when we consider vectors related by the pushed forward operation. We can generalize this to tensors of higher rank, but as we will see, this will be possible only for tensors whose indices are either all down or all up. These are tensors of type 0L or L0. For mixed tensors, phi needs to be invertible, which is an assumption that we don't make in this video. Therefore, we will discuss how to carry along tensors between the manifolds only in the case where we have 0L or L0 tensors. So let's start with 0L tensors. So that's a generalization of the one form that we discussed before. So let's see what we have. We have the map phi. We have the push forward map that takes the vector v here to a vector phi star v at the point Q. And now we will define a map that takes a 0L tensor at the point Q to a tensor phi star t at the point P. We will do that the obvious way, using the push forward of the vectors. So in order to define the tensor, we have to know its action on any chosen vectors at the point P. So the action of phi star of t on those vectors is equal to the action of the tensor t on the pushed forward images of the vectors v. Then we can compute the components of such a tensor. The computation is easily generalized from the case of one forms. The only difference here is that we have a derivative factor here, one for each index of the tensor t. This is a linear operation, and we see here that the same linear operator is involved in transforming the components of t to the components of phi star of t. A special case are 0,2 tensors, and we are especially interested in tensors that are metrics. So if we have a metric on the manifold n, that will define a metric on at the point Q. So we have a 0,2 symmetric non-degenerate tensor at the point Q, and we want to see what is its pullback under phi star. So we use the definition that we described in the previous slides. Any vectors v and u are mapped under phi star of g to the image of the pushed forward vectors phi star of v and phi star of u. Note that phi star of g is not necessarily a metric at the point P of m. Let's compute the components of this pulled back tensor. Here we use the formula that we derived before for general 0L tensors. Now L is equal to 2. So we have here the matrices phi star. Now we move this one here and sandwich G between the two phi star matrices. And now we want to exchange the order of these two indices, nu and beta, and make it beta nu, so that we have a matrix multiplication. You see, to have a matrix multiplication, this has to be summed with this index, and this has to be summed with that index. But in order to do that, we need to consider the transpose matrix of the representation of phi star. So, if we actually want to do such a computation, we have to take the metric G, arrange it into an n by n matrix, and multiply it from left and right by phi star, an m by n matrix, and its transpose, an n by m matrix. That will give us the components of the pullback of G arranged in m by m matrix. Let's note here that in the case where n is a higher dimensional manifold than m, then the map phi is an embedding of m into n. In that case, if the pullback phi star of G is non-degenerate, then phi star of G is a metric on m. This is a special metric which we call the induced metric on m by the function phi. Now let's move on to tensors where all their indices are up. These are L0 tensors. Now we will discuss the push forward of such tensors from the point P to the point Q. So let's consider any such tensor at the point P, and we will denote the pushed forward map of it as phi star of S, as before. To do this, we will use the pullback of one forms from the point Q to the point P. And since such tensors are defined by their linear action on one forms at the point P, we can make this action to be equal to the action of the tensor S on the pullback images of the one forms of metal. Then we can compute the components of the pullback of the pushed forward tensor. Sorry, I was saying pullback, but it's push forward. Sorry, S is pushed forward from P to Q. So the components of this pushed forward tensor is given by a similar relation like before, but notice that the indices are now arranged in a different order. So we have to have alpha here, and we have to have nu here, so that we can use the matrix dy over dx, where alpha is upstairs and mu1 is downstairs. So this is a linear operation involving the matrix representation of phi star. As a special example, let's consider coordinate vectors. If we have a coordinate system in the neighborhood of P, that defines a coordinate basis which we denote by d mu. in this basis, the components of those vectors are trivially given by the Kronecker delta mu nu. Then, using the formulas that we described before, the component of the pushed forward image of the mu is given by the derivative of y with respect to x. So that this vector here, as a linear combination of the coordinate basis in the neighborhood of Q, is given by this relation. Another example is to consider embeddings. And just to be more specific, let's consider embeddings of two-dimensional surfaces into the Euclidean space R3. So, in this discussion, m is equal to 2 and n is equal to 3. This, for example, could be the embedding of a two-sphere into R3. And since in R3 we can use the Cartesian system and have Cartesian coordinates, which we denote by the vector y, each point here of the surface will be a function of the coordinates x mu of the surface. Then it's easy to see from this relation here that the components of the coordinate vectors in R3 are given by the derivatives of those functions dy over dx mu. Let's also consider one forms that come from coordinates. So in this case, the pullback of those forms is defined. So we need to consider a coordinate system in the neighborhood of Q that defines coordinate one forms, which we denote by dy alpha. And these are pulled back by phi star to the phi star dy alpha. The components of dy alpha are trivially given by the delta Kronecker delta alpha beta. Then we can use the relation that relates the components of the two vectors here, and we see that the components of phi star dy alpha is given by the derivatives of the coordinates y with respect to x mu. And we can write the pulled back one form, phi star dy alpha, as a linear combination of the coordinate one forms at the point P. This is another very simple example where we consider the manifold M to be the plane with the origin removed, and the manifold N to be the circle S1. We construct a very simple map between the two by placing the circle with center at the origin and considering rays starting from the origin. Then a point P on the manifold M is mapped onto a point Q on the circle by projecting P on the circle on this ray. Mathematically, we can express this map by considering the r theta coordinates of the point P. Then the point Q will have coordinate phi, where phi is equal to theta. Then we can remember the elementary relation that connects the coordinate vectors dr and d theta to the unit vectors, the Cartesian coordinate vectors dx and dy. From this relation here, we see that dr is not a unit vector, but has modulus equal to r. but d theta is a unit vector. In that case, the unit vector ER of the manifold M is 1 over R times dr, whereas the unit vector E theta is equal to d theta. And you can see this situation here in a simple geometric representation. Then we will see that the push forward of the vector E theta is d phi. And since E theta and d theta are the same will be true for the push forward of the vector d theta. The vectors ER and dr, however, are projected out, and their image under phi star is the zero vector on S1. To see this, let's consider an arbitrary vector at the point P, whose components with respect to the bases dr and d theta are Vr and V theta. Then we can compute the component of the pushed forward vector phi star V. It is given by this relation, but since phi is not a function of R, this first term here vanishes, whereas this term is equal to 1. Therefore, the unique component of this vector is equal to V theta. Then you see that the pushed forward vector phi star V is equal to V theta times the coordinate vector d theta. And if we want to make a simple representation here on the plane, you see that in order to obtain this vector, all you have to do is to project V into the tangential direction on the circle S1. So this component vanishes and this component remains.